I assume we'll connect with some of the questions that were so the topic that I'll be talking about indeed first is a deformation of two-dimensional CFT that's called the Tt Bar Deformation. Again, many of the questions that have to do with quantum information are motivated indeed by the idea of bulk reconstruction, the fact that we want to understand gravity, and if we have a quantum system like the CFT where we know that the quantum rules apply, then essentially the question of how quantum information behaves in gravity is the question of bulk reconstruction. And the Tt bar deformation is a way of deforming a CFT where you have to essentially start thinking about how the boundary connects with the bulk in ways that give interesting lessons. And indeed, the first part of my talk will indeed be a lesson that will come from studying this Tt bar deformation. And if I have time at the end, I'll make also some comments about the SYK model. So indeed, I'll talk a bit about causality, and part of the other middle part of my talk will be actually the question whether this Tt bar deformation actually has a precise definition, and I'll make the case that the Tt bar deformation indeed has a precise non-perturbative definition. So for those of you who missed Peter Shor's talk yesterday, there's this apparent paradox or contradiction between two common notions about black holes. Indeed, light slows down near a black hole. The light cone squeezes near a black hole horizon. If you draw the light cones in Schwarzschild coordinates, they look roughly like this. And indeed, motion stops at the horizon from the point of view of the outside. And that's indeed indicated by this blackening factor that stands in front of the time coordinate in the metric. At the same time, there's the law that if you look at the quasi-normal behavior of a black hole, you find that there's this characteristics time m log m. If we believe in holography, then a black hole is made out of stuff, and the equilibration of the black hole in this enormously short amount of time should be interpreted as a thermalization. And indeed, there is the law that this thermalization for a black hole happens very quickly in this scrambling time, which actually was identified a number of decades ago already as a characteristic time where the physics of black holes becomes basically non-perturbative in some ways. But the contradiction is indeed that it's very hard to imagine how, by causal propagation along a membrane horizon, one could imagine this thermalization happening that quickly. And indeed, partly actually as a consequence of things we learned from the Tt bar deformation. I gave also a talk already 2 years ago where I asked this question: can quantum information travel at warp speed precisely with the same sort of motivation? The black hole thermalization seems to happen relatively quickly, compared, or at least too quickly, compared to the causal structure near the horizon. So let me again say some things about this Tt bar deformation and why it's interesting from the point of view of holography. So schematically, again, you can take it as a two-dimensional CFT and deform it by turning on a coupling that looks like this, where T is the stress tensor, and it means that the operator T times T bar has dimension 4. So this is a deformation, but it's an unusual one. It's an irrelevant deformation. And actually, you could even argue that the word deformation might be a misnomer, because in some ways, when I start with a theory on the right with mu non-zero, it's possible to take the limit from mu to 0 and get a CFT, because mu is the only scale in the problem. But it's less clear that you can actually do perturbation theory in mu and view the theory on the right-hand side really as a perturbation of the CFT. Again, this subject goes back actually to earlier papers, even by Samolojkov maybe 15 years ago. But indeed, in these three collaborations, people defined this theory in a way, or at least studied this theory in a way where you could get this remarkable property, essentially, that you can solve for the energy spectrum of this theory on a cylinder. The reason I got motivated in it to study it had to do indeed with some intuition where I felt that there had to be a connection between this deformation and moving essentially the CFT into the bulk, or looking at boundary conditions in ADS space that are not just asymptotic ADS boundary conditions, but where you keep the conformal factor of the metric finite. But another sort of thing that triggered my attention was a study by Cardy, where he indeed looked at the Tt Bar deformation and just made, of course, the natural comment that the product of Tt bar through a Hubbard-Stratonovich trick can be written as the result of doing a Gaussian integral where you have basically turning on and off diagonal component of the metric, and you assume that it has a Gaussian fluctuation, and then if you integrate out that off diagonal component, you get back the Tt bar deformation. So in that respect, you can already see that this Tt bar deformation in some ways is actually more like coupling the CFT to gravity, and that you already get some form of non-locality already in the CFT space-time itself. And another thing that you're going to be seeing is that this Xi deformation indeed starts separating out two versions of a light cone. One is the fixed metric, and the other one is the fluctuating metric that's parameterized by Xi. Earlier studies of the same theory, again, these papers basically pointed out that this Tt bar deformation appears to be integrable. And one way of defining it is that if you would start out with a theory that's not initially a CFT, but you think about the CFT as the mass to zero limit of a two-dimensional integrable field theory with a factorizable S matrix, then there's a deformation of the 2D QFT with what's called a CDD factor, where you change the S matrix, the factorizable two-particle S matrix, by just adding this particular phase. But that phase is momentum dependent, and it essentially tells you that the left movers and the right movers are interacting with a shock wave. Analogous to the shock waves are actually the two-dimensional version of the shock wave that happens near black hole horizons, and that give rise to the chaotic behavior. So this is a gravitational interaction. But it turns out that this one preserves integrability. So that gives an indication that the theory might be well defined. But the thing, again, that, as I mentioned, that drew my attention at the time was that if you take, again, this Hubbard-Stratonovich representation, which I mentioned represents this fluctuating metric, then if you look at the system at finite temperature, which is supposed to be corresponding to a black hole in the bulk, then even from the point of view of the boundary now, something funny happens, namely that if the stress energy tensor gets an expectation value, which it will at finite temperature, then this means that if you do the Gaussian integral, that the saddle point for this variation Xi will be proportional to the expectation value of the stress tensor. And therefore, when you turn on temperature, this saddle point metric will start back reacting in terms of the expectation value of T. And then, hey, it seems that also that then as a consequence that the speed of light starts changing, because if the light cone back reacts, then turning on stress energy will make the speed of propagation change. So I thought, well, hey, this looks nice. You have a change in speed, propagation speed. And then I wanted to compare that indeed with what happens indeed with this blackening factor that I told you about, the fact that light cones are squeezing. And that thing indeed precisely matched with other comparisons that we had to make between the interpretation of moving this into the bulk. So I thought, well, hey, here I can see that light is slowing down when you approach a black hole horizon. That's the squeezing of the light cone. It turned out actually, since signs are not my strength, it took me a couple of months to figure out that actually the sign that I needed here was actually a plus sign. So it was not something that I decided to just adopt as an assumption. It was a conclusion that came out from the study. So again, at that point, you have to start thinking, because then it means that apparently, if you want to make this comparison with the bulk, you have to start thinking about things that might be superluminal instead of subluminal. Of course, whether if something is superluminal or subluminal is just a relative statement. If you have two light cones, one of them is bigger than the other, and one of them is called then superluminal relative to the other. So it turns out that in this case, actually, in some ways, relative to the original fixed metric, the fluctuating metric is superluminal. So what fixed the sign? In this case of mu, the thing that fixed the sign was that, as I mentioned, the spectrum of the Tt bar theory can be computed. It turns out also that people had already computed the spectrum of ADS spacetime in a finite box as a function of the size of the box. If you have a black hole of a certain mass m, you can compute the energy by integrating the total York-Brown stress energy tensor on the boundary. And it turns out to be given by that formula up there. You see a square root. Again, it comes out of the calculation. But you see a 1 minus mu times the mass. So m is the mass of the original black hole. But the effective energy of the black hole in the box is depending on the volume, on the radius of the cylinder, which is r. But something funny happens when, say, if j, which is the spin of the black hole, is 0, then if mu times m is equal to r squared, that square root becomes 0, and afterwards becomes imaginary. So that's a funny point. But that's precisely the place where the horizon of the black hole touches the boundary of the black hole, the boundary of the box. So you should expect something funny to happen. But it turns out, again, that with that identification, mu being that relation between the size of the box and mu being the deformation parameter of the CFT, you could actually make a match between the Tt bar deformed energy spectrum and a black hole in a box. So it turns out also that there was an earlier work by Don and Mukund, who indeed had identified in this particular situation that there are indeed modes in gravity that propagate faster than the speed of light from the point of view of the edge of the box. So there's a light cone on the box, but gravity with Dirichlet boundary conditions in a finite volume with a black hole in it has modes that go faster than the speed of light on the boundary of the box. Now, at some level, that's not a surprise. If I give you a cylinder, I can go faster from one side to the cylinder to the other side of the cylinder just by going through the interior. Going around is inefficient. But this effect is actually much more dramatic than that. So this is not just taking a shortcut. There's really something happening in the gravity in the box that, from the point of view of the boundary of the box, looks superluminal. And indeed, the computation here actually turns out to be such that the propagation of modes inside of the cylinder goes with the speed that happens to be the speed of light of the original CFT. So the speed of light on the boundary of ADS, although the boundary is no longer part of this geometry, is the thing that determines the propagation speed of these modes. But from the point of view of the local geometry, that's superluminal. And finally, there's an argument, again, with Mark and Douglas. There was a study of thermalization, which indeed is precisely the problem that was also discussed in yesterday's talk. If you, now, if vertically is the radial direction, the blue line is the actual original ADS boundary. We're imagining that we can put the black hole in a box where there's some finite radius r equals rc, where we have some theory living, which is the Tt bar deformed theory. And you could ask, how quickly does information spread? And then you can do an experiment. If you assume, indeed, that the entanglement wedge reconstruction works, that if you take an object in the bulk and you want to know where is the information in that object contained in the boundary, then what you do is you make a root Toginagi surface and you make sure that the object in the bulk is within the entanglement region surrounded by the Ryu-Togenagi surface. And indeed, if you take then an object that falls into the black hole, and you track how the Ryu-Togenagi surface has to behave, which is this black line, as a function of time, you'll find that these endpoints, the two endpoints, have to propagate with the speed of light on the boundary of ADS. Which actually means that on the cutoff surface, because basically this Ryu-Togenagi surface goes straight out from basically to the horizon to the boundary, from the point of view of the cutoff surface where the light cones have been squeezed, that speed at which it's propagating is superluminal. And the interpretation of this is that this particular region inside of the Ryu-Togenagi surface is the region that you have to have access to in order to reconstruct the information of the infalling object. And that region, again, seems to propagate superluminally. And finally, there's one third argument, or fourth maybe, namely that if you imagine that you can put the black hole in a box, the black hole is very hot. If you make the box very small, the pressure inside of your box gets very big. And if you compute the speed of sound in that particular fluid, that speed of sound will again have a factor that will make it bigger than 1 relative to the speed of light. So there are many arguments actually that indeed something is going on near the black hole horizon where the light cone has sort of two meanings. One definition of the light cone is what is signal propagation, and the other, there's another light cone in the story which you could call the butterfly light cone perhaps, which has to do with how information spreads out. The apparent contradiction between this and relativity is, okay, well, if information can spread faster than the speed of light, okay, what about causality? Can't you kill your own grandmother? The point here is that the green light cone, the butterfly light cone, is one that corresponds to diffusion of quantum information. And it's possible to essentially diffuse quantum information without actually sending it. Meaning, if you use this quantum secret sharing idea that you have information locally, but you can split it up into small little chunks, send all these little chunks in different directions, and no one who receives any of these chunks will know anything about the information. You can spread it, you can diffuse the information arbitrarily, and therefore only someone who would have global access to the complete state in this case within the green light cone, would be able to reconstruct the information. But that's not the same as signal propagation. So that could be a way out. Now, there are still many questions. This should be a motivation, at least, for studying whether the Tt bar CFT actually, Tt-formed CFT actually makes sense. Andy, yes?
Is that some kind of non-local operator spread around the outside of that light cone? The butterfly velocity won't commute with a local operator?
That's right. If it's non-local, if it goes all the way around, it wouldn't commute. That's right. But that's the same in ADS CFT. If I take non-local operators on the boundary, it doesn't commute with anything space-like separated in the bulk. So that's not, in that aspect, not surprising. So at some point, there was a belief that Tt bar deformed theories may not be well defined. Indeed, it looks kind of suspicious. Indeed, if you try to do perturbation theory with Tt bar, you run into problems. If you do conformal perturbation theory at the second order mu, you basically have to do integrals that are diverging. So it's not clear if as a perturbation it's well defined. But it was already pointed out by people earlier that in the special case of C equals 24, if your CFT has central charge 24, there's an equivalence between the Tt bar deformed theory and basically just the world sheet theory of a Nambu-Goto string. What you do is you take your C equals 24 theory, you couple it to light cone coordinates. So this doesn't need to be 24 bosons. It can be any C equals 24 theory. It doesn't need to be chiral. It's some complicated theory potentially. But the deformation is described by coupling it to the two bosons. And you just impose Virasoro conditions. And since you have conformal invariance, you can use, again, this temporal gauge. And in the temporal gauge, this Virasoro condition simplifies. One of these factors becomes equal to 1. And then the other coordinate is just the integral of the stress tensor. You plug that back in there, and that becomes the Tt bar deformation. And then indeed you can see that the spectrum of this theory corresponds to that of Tt bar. Again, the spectrum of the Nambu-Goto string would be the sign of mu that's just the opposite one than the one I just discussed. It's the one where the light cone is squeezing. But okay, first I want to study indeed whether the Tt bar theory is well defined. And for C equals 24, there's no reason why it would not be well defined. It's just equivalent to coupling the CFT to a free boson and imposing Virasoro conditions. Let me do it a little bit more sophisticated. First of all, if I want to put the theory on a cylinder, by the way, I should not do the cylinder just on the world sheet. My target space coordinates, which is x plus and x minus, are really the coordinates on which the Tt bar deformed theory lives. So my target space indeed would have to be a cylinder as well, and I have to be in the winding number 1 sector in this theory. So this is my target space. I write down a BRST charge of the sum of the two theories, the CFT and the x plus minus CFT, and I define the BRST cohomology. That the BRST charge squares to 0 because C equals 24, plus 2 is of the x plus x minus. This is a critical string, and I can define the BRST cohomology. And this gives me a non-perturbative definition of the theory. And then I just have to ask, okay, what kind of observables do I have in the theory? And now I can start doing computations. And most of those computations you can find in old string theory books. How do I go? Oh, by the way, what happens if I flip the sign of mu? Flipping the sign of mu corresponds to flipping the sign of the kinetic term, which is flipping the x1 and x0. So the wrong theory sign corresponds to this theory, where actually, indeed, sort of the time-like scalar field is now compactified, and the space-like theory scalar field is non-compact. If I compute the Hilbert space in this particular theory, I still get a well-defined Hilbert space. So personally, again, I'm agnostic about whether the wrong sign of mu gives me trouble or not. At this point, I'm not seeing the trouble yet. I'm nervous because my string time coordinate is periodic. But from the point of view of the definition of the theory, I don't immediately see a problem with it. Theory is ghost free, right. The BRST, there's no negative norm states. The no-ghost theorem goes through. So well defined. So this is C equals 24. Now you could say, well, okay, maybe C equals 24 is special. What's going on with those other values of C? It's not so hard, actually. Andy just walked out. He comes back in. There's a way of doing non-critical string theory, which is a bit similar to what Andy and Joe Putinsky did a long time ago. This is actually a simpler version of what they did, because essentially what I can do is I can take this light cone part of the string theory. If I don't worry about 26-dimensional Poincare invariance, but I only worry about 2D Poincare invariance of the x plus x minus direction, there's a very easy way of making this string theory non-critical. What I'm going to do is I'm going to add what you could call a background charge. By the way, you can think about dx plus dx minus as two, again, your target space coordinates. You can think about the product of dx plus times dx minus as a two-dimensional metric, and it's a flat metric. And indeed, it turns out that this particular theory is equivalent to a version of what might be called Shakif-Teitelbaum, although it's actually more like CGHS, that if you take this particular theory where you have a dilaton that imposes a flatness of your metric, and you just have a cosmological constant, this theory turns out to be equivalent to this theory. If you indeed add also a Liouville part of this flat metric so that this theory can have general central charge. And that's what this theory corresponds to. Notice the following, that if I take my background metric to be flat, so R here is the Ricci curvature on the world sheet, I can take R to be 0. And this is still a Gaussian. I can do all my computations with Gaussian integrals. It's a free field theory. Okay? The only thing is that my definition of my stress tensor now has an extra piece because of that background charge, which looks like this. And you can easily do a computation showing that this theory has a central charge given by a general C over 24, different from 1, but swifted by that number Q. Yeah.
How this resolves the initial problem with Tt bar being an irrelevant operator and leading to divergences? That's somehow fixed here or not?
So the thing is that I'm not going. What I'm saying here is that already at this point, I wouldn't necessarily know if I couple this theory to a CFT, and I take the BRST cohomology of the combined theory, that I should view that as a deformation of the CFT. It's a different theory. Later on, I'm going to put mu equals to 1 because it just sets my length scale, and indeed I have another scale, which is the cylinder. But essentially, it's a different theory, and turning off mu might be possible. It's like the alpha prime to 0 limit. We were talking about string theory earlier. In this case, turning mu off is like taking alpha prime to 0. Okay, well, is string theory a deformation of Q of T? So is Tt bar a deformation of CFT? I don't know.
Is that term breaking parity thing? Because you have a connection between the...
Yeah, so the world sheet parity and the target space parity are connected.
But that's not true in the...
That's why wouldn't that be true? Again, there's only one coordinate system in if I flip, because yeah, in Tt bar you don't see the two systems, but this works fine. So okay. So again, you can this thing looks a little bit unfamiliar, but you can rather easily do OPEs with this thing. One interesting calculation is to take the OPE of this thing with a standard vertex operator, e to the I px. Then what you're going to find is that if this thing has an OPE with e to the I px, the vertex operator will shift this thing by an amount p over the distance to the vertex operator, p over z. It's behind the logarithm. And if I differentiate the 1 over z, the log of 1 over z twice, I get a q over z squared term. So what you're going to find is that the only effect of this term for vertex operators like e to the I px is that it shifts the conformal dimension by amount q, which is c over 24 minus 1. And indeed, the consequence of this is going to be that the on-shell condition will be shifted by c over 24. And this is precisely what happens indeed in the spectrum of the Tt bar theory. So I claim that this theory, through the same argument as the previous slide for the C cos 24, it should be equivalent to the Tt bar deformation. Poincare invariance indeed is preserved. Okay, how much time do I have? 5 minutes, okay. So now we would like to compute correlation functions such as the two-point function. Now it's not entirely obvious that in the Tt bar deformed theory there should be such a thing as a two-point function. Again, the correlation functions of the stress tensor can be analyzed quite explicitly, and they actually match with the various proposed dualities or prescriptions. This two-point function is something that hasn't been really defined in the Tt bar theory, and I'm going to give you a proposed definition for it. So in position space, I could take two primary fields in the CFT and ask, okay, what's the two-point function? And now I want to do the Tt bar deformed version of that. Or I can go to momentum space. And naively, at least if you follow your nose in string theory, you look for a physical operator, and you take a dimension 1,1 operator, you integrate it over the surface. That's a physical BRST invariant operator. And there's a corresponding state in the CFT, which is part of the BRST cohomology. And as I mentioned, again, for general central charge, the only place modification that you need to do is over here. So this is a way of computing two-point functions, but it's slightly disappointing because I cannot really do an off-shell two-point function. I cannot localize operators because p squared has to satisfy the massless shell condition. I can only do on-shell computations in the x plus x minus plane. So the question is, can I do something with off-shell correlation functions? This problem that physical operators are on-shell and that I only can do on-shell calculation, for me immediately brings me back to the 1980s, the early 1990s in string theory, where for many years we would only know how to do on-shell calculations in string theory. So if I ask, okay, well, is there a way of going off-shell? There's a natural idea. Maybe then, rather than me telling it, does anyone have an idea? I think 1995. You may want to do something with D-branes, where indeed you try to have an operator that's localized in x plus and x minus. But rather than thinking about it as vertex operators, we should introduce a boundary. And we should allow the worldsheet of the Tt bar theory to have a boundary in the target space. So, so here's a concrete proposal. You could indeed, rather than multiplying an operator with a vertex operator, I can take the Ishibashi state of a particular operator, multiply it times a boundary state. In momentum space, it could be an Ishibashi state with a given momentum eigenbasis, value. Or indeed, in position space, if you Fourier transform this operator, you essentially are localizing the zero mode, you're localizing the x plus x minus field at a given location in space. And therefore, it's in space-time. It's a local operator, but on the worldsheet, it creates a hole. By the way, having been here before, of having thought about bulk operators previously in terms of boundary states, this is indeed an idea that came up earlier. In this case, again, it came out of trying to look for off-shell operators in the Tt bar theory, but in the in this case, again, it's still a relatively radical proposal because it kind of it cuts a hole in the worldsheet. But in the target space, it's still a local, potentially a local operator. But when I say local, of course, I don't mean literally local, because there's no reason for why in the Tt bar theory we would literally assume that things can be local. And indeed, you would expect that these operators, when you start doing computations, will essentially correspond to a finite size object. And indeed, by inserting that boundary state in the worldsheet of the Tt bar theory, you're introducing a new modulus, which is the size of the boundary. And the computation that we already started doing is to indeed start computing correlation functions of these operators. And then what you're going to find is that depending on the configuration of correlation functions, that the size modulus of this boundary state, you would have to integrate it over it. But in the small mu limit, that integral has a saddle point that essentially fixes the size of these objects. And then indeed, you start having the equivalent of off-shell operators. Partly of having been here before, let me also put out another possibility that instead of doing the D-brane type boundary conditions, which would localize the boundary state at a point in space, there's also another option where you work with cross-caps, where you take indeed a cross-cap boundary state. And both of these in the mu to zero limit effectively should correspond again to local operators in the CFT. 2 more minutes. Are there questions at this point? So this is a computation we're still doing. This is a comment about a proposed definition of the Tt bar CFT. CFT. Yes?
Do you have the expectation value of the stress tensor turned on, or is this in the way?
So the definition of the local operator, of course, could in principle be done in the presence of other operators. But at this point, I'm assuming that theory, again, lives on this cylinder. Whatever I'm doing with expectation value is determined by the initial state. So there is actually an operator that acts here, which, for example, creates the winding number. But again, in the bulk, I'm imagining that everything is flat. So obviously, the target space is flat. OK. I will not say too much about this thing. Again, this is going to be a comment. Maybe it's actually sort of a commercial for a paper by other people that appeared, I think, last week by Berkos, Naravlansky, and 2 collaborators, who in my mind did something quite interesting with the SYK model, which in part because of remarks and also by Alexei and relations with earlier work that I've done with collaborators over the last few years, seems to indicate that there's actually a 3-dimensional perspective on SYK. So let me very quickly go through that. So often when people write down correlation functions, we work in position space, or we talk about out-of-time ordered correlation functions and things like that as a function of time. And then we get this Lyapunov behavior as a function of time. But very often when you study things in a quantum mechanical system, it's very useful to have a spectral representation. So for example, if I take a 2-point function in SYK, I can try to represent it as an integral over a variable that here I'm calling K, which is essentially the energy of the intermediate state. So if I have 2 operators at tau 1 and tau 2, I can represent the 2-point function as if it's a boundary-to-boundary propagator, but then they're intermediate states with energy, and I'm going to project on a given energy. I get a partial wave, and the total correlation function is an integral. In the case of the Schwarzschild theory, if you take the Schwarzschild limit, you can actually compute this partial wave, and you get an answer. The explicit answer here is not important. It turns out that if you work with in-time ordered correlation functions, you can generalize this 2-point function to higher endpoint functions, and effectively you get a set of quote-unquote non-perturbative Feynman rules where every intermediate state which propagates over a certain amount of time has a corresponding propagating factor, which is just e to the minus t times the energy. Every time you have an operator insertion, there's a corresponding matrix element, which is known in the Schwarzschild limit. But in SYK, one is mostly interested, at least in the fact that it's a chaotic system. And one can probe that famously, indeed, with the out-of-time ordered 4-point function. The in-time ordered 4-point function directly follows from this expression for the 2-point function for the Schwarzschild limit, again, just by these diagrammatic rules. But when you go to out-of-time ordered correlation functions, you get a new phenomenon that you have to basically switch 2 operators. And since the operators of the same type are connected by a propagator, switching 2 operators leads to this crossing. And this is a figure in an earlier paper. I'm going to point to the whole point of this last comment actually is over here, where I didn't draw the connected line here, which in the case of the Schwarzschild actually is a misrepresentation of the actual structure. I can actually just draw these lines, and there's no ordering involved. But as soon as there is actually an ordering involved in whether one overcrosses or undercrosses, then if this is a 2-dimensional plane, I'm already assuming that there's a third direction where I can actually see whether this thing overcrosses or undercrosses. And there's the question whether in SYK there's actually a notion of an overcross or an undercross or not. And a priori you might think not. And indeed, if you go to the Schwarzschild theory, it turns out that you can actually relate the 2 types of partial waves for the out-of-time ordered and the in-time ordered correlation function by an R matrix, which is just a redefinition, a basis transformation, but it's some unitary transformation that depends on all these labels. And just almost by representation theory, this R matrix is a 6J symbol of SL2R. But in this case, actually, that over and undercross actually doesn't matter, because it's a classical group. Now, what's actually quite interesting about the results that were obtained recently in a particular double-scaled limit of SYK, where you take psi to the q which actually in the authors call psi to the p, where that's the psi to the p interaction of the SYK model, where you take p to infinity, p squared over n finite, and then you're going to get a number that you call q, which is e to the p squared over n, which is kept finite. And what's interesting is that the answer that you're going to get is almost identical to an answer that we already found 4 years ago by studying gravity in 2 + 1 dimensions, where we actually had the same combinatorial way of looking at out-of-time ordered correlation functions. And then that particular R matrix turned out to be the 68 symbol of a quantum deformation, a Q deformation of SL2R. But the Q deformation is precisely different from the ordinary group in the sense that it actually has an R matrix that cares about the ordering. So this is a 2 + 1 dimensional perspective on this R matrix, but it's not identical to the Schwarzschild. The Schwarzschild is a limit where this ordering seems to have gone away. But the surprising thing of the work by Berkos et al. Is that they found essentially almost the same thing as that, as an exact result in SYK, except that the quantum group they have is not UQ-SL2R, but UQ-SU11, which is almost the same thing, but not quite. But nonetheless, that R matrix that they found has that overcrossing feature. So just as a last comment, this gives an indication that the bulk dual of SYK may actually have a 3-dimensional interpretation, because that's where the overcrossing should be coming from. And this is, of course, the same overcrossing and undercrossing that led to the step from WCW models to Chern-Simons as a 3D perspective on the Jones polynomials. Okay, thank you.